Okay, good afternoon and welcome to the European and Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Professor Kaiming Zhao from the Wilfrid Laurier University in Waterloo, Canada. The title of his talk is Characterization of Simple Smooth Modules. Please.
Yeah, thank you very much. I'm honored to give this talk here. And yeah, I'm in my hotel. Yeah. Okay. Today I'm going to talk about characterization of simple smooth modules. So let's see. This talk is based on a preprint. We just finished last January with 3 of my co-authors. Yeah. So basically, I will talk on these 4 topics, 4 sections, and let me start with section 1. So a little bit of history on smooth modules. We denote Z star, N, Z plus. Those are just the standard notations, and particularly this N is, let me see, corresponding to non-negative integers. Z plus, this is the set of yeah, N is non-negative integers. Z plus, the set of positive integers. Yeah, all other notations are standard. So let me give you the definition for a smooth module. So we have a Z-graded Lie algebra, this G. A G module V is called a smooth module if for any small v in V, we have a integer n such that Gi acts on V is equal to 0 for all I bigger than n. Yeah, the category of smooth modules over G will be denoted as we use the script R sub G. Okay, we're going to study this kind of modules. So yeah, well, the definition for finite dimensional algebras is meaningless because for a finite dimensional algebra here, so you have only finitely many GIs, non-zero GIs. Okay. So in general, so we're familiar with highest weight modules and Whittaker modules. Those are highest weight modules and Whittaker modules are smooth modules by definition. Okay. Well, if you take proper gradation, Z gradation. Okay. A little history. So modules for affine algebra, let's see. This smooth modules for affine algebras are, let me see, are studied by Kazhdan and Lusztig in these 2 papers. It's just 30 years ago. And later, Yakimov gave some results also on affine Kac-Moody algebras. Here, yeah, this is the exact, well, yeah, this is exact smooth modules for affine algebras. They use the gradation for D, the derivation, okay, or with respect to the variable t. Okay. Okay. Well, actually, there are some studies on simple smooth modules over some Lie algebras. So here are some, yeah, for example, for affine Kac-Moody algebras, I mentioned this. For Kazhdan type Lie algebras over formal power series, over Waterloo algebras, the Waterloo algebra, the Waterloo superalgebras. We have 2 Waterloo superalgebras. The twisted Heisenberg-Waterloo algebra, the Schrödinger Waterloo algebra, and the mirror Heisenberg-Waterloo algebra. Well, we have more, like W22 algebras. So we have results. We have some studied on simple smooth modules over those Lie algebras or Lie superalgebras. Yeah, more details. Actually, Rudakov studied simple continuous modules over Lie algebras of Kazhdan type WSH over formal power series in these two papers. Those are old papers. Okay, almost they're 50 years ago. Okay, so they consider those Lie algebras over formal power series because those algebras have a good topology. Okay, good topology. Or so they consider continuous modules. Those modules are actually exactly smooth modules, corresponding to the gradation, the Z gradation. Okay. Now let's look at the Waterloo algebra. The Waterloo algebra is an infinitely dimensional Lie algebra with basis C, D, N. This N is running over Z. And the Lie bracket is given by those. The first line tells us C is the center. And dn bracket is equal to m minus n times dm plus n plus here m cubed minus m divided by 12 delta m plus n 0 c. All those mn are integers. This is a standard Waterloo algebra. In some cases, they use n minus m. Well, they are isomorphic. Okay. So this is the famous Waterloo algebra. Yeah, let's consider the twisted Heisenberg-Waterloo algebra D. Okay. Now this algebra has basis. We have this dm. Well, we have HR, C1, C2, C3, m and r are integers. The brackets are given by the following. Okay. The first line tells us dm C1 is the Waterloo algebra. And dm acts on HR. It's just minus r times h m plus r. And you have this center C2. HR HS, the bracket is equal to R delta R minus S C3. Well, the third line tells us H and C3 form the standard Heisenberg algebra. Okay. Now C1, C2, C3 are the center. Actually, this algebra has one more center, so H0, right? H0 is also in the center. Okay. So it has four-dimensional center. Okay, H0, C1, C2, C3. Let's consider the mirror Heisenberg-Waterloo algebra. Do I use D? I use the same D. I should put a bar or tilde. Okay. Now this time, we have exactly the same definition, almost, if you ignore the center. And now this time R is only integer plus 1/2. That is the difference. The bracket says the first line tells us D and C1 form the Waterloo algebra. And dm acts on HR, the same action without center. H and C2, they form the standard Heisenberg algebra. Okay. Now this algebra has two-dimensional center C1 and C2. Here we don't have H0 because R is integer plus half. Okay. Yeah. Now we need basically I use D to denote this mirror Heisenberg-Waterloo algebra. Okay. This is our D, not this one, not the twisted Heisenberg-Waterloo algebra. Okay. So I use dmn. M, that means the index for D is bigger than or equal to M. n means the index of H is bigger than n, Yeah, this I can be 0. Yeah, at least the index at least is n plus half, right? Yeah. Okay. Now simple smooth modules. Yeah, let me tell you more. What for what algebras we know the simple smooth modules. Okay. Yeah, here in this paper by Mazurchuk and myself, we determined all simple smooth modules over the Varsova algebra. Yeah, the result is as follows. So any simple smooth module over the Varsova algebra is the highest weight module or isomorphic to the induced module for a simple where R plus module V, such that for some positive integer k, not positive, non-negative integer k, no, this is positive. This is positive. Positive integer k. This decay acts on V injectively. All di on V is trivial for I bigger than k. Okay. Basically, this V is a simple module over a finite dimensional algebra, a solvable algebra. Okay. Then we have the induced module. If V is simple, this module is always simple over the Varsova algebra. But certainly, you can see if D is 0, the result we would get a highest weight module. Clearly, the induced module would not be the highest weight module would not be simple. We have a lot of we have the criterion for highest weight module to be for the Wurman module to be simple. Okay. This is one. The algebra we know all the simple smooth modules. Okay. Now let's consider the Varsova superalgebra S. Well, this is called what is that? Neville-Schwarz superalgebra. This is one of the Varsova superalgebra. S has a basis this Rm GP C, and M is running over Z. P is running over Z plus half. Okay. We have the L and C. Those are even part, and this G are the odd part of the superalgebra. This S1. Okay. The brackets are given by the following. Again, the first line tells us Lm and the C form the standard Varsova algebra. Rm acts on the bracket Rm GP is simply m over 2 minus p times GP plus m. So GP bracket is equal to 2LP plus Q plus, well, you have a multiple of C. And the C is the center of S. Now here the bracket is a super bracket, because these two elements are odd. Okay. This is the Varsova superalgebra. Now, I still need a little bit more on this algebra. As is, we have the triangular decomposition, and we have the Z half Z gradation. This S is S plus, direct sum S0, direct sum S minus. So S0 spanned by L0 and C. S plus, say here now L is the index. The index is always positive, and here the index is positive, that is S plus. Similarly for S minus. Okay. Well, we have this standard gradation. Each homogeneous space Si is one-dimensional, except for S0, right? S0. Yeah, if I is integer, Si is spanned by Li. If R is integer plus half, is spanned by GR. Okay. Yeah, we need to define this SM. SM, that means the index of L is bigger than or equal to M, and here the index of G is bigger than or equal to M. Okay. And also you have this center, that is our SM. Yeah, I need this SM to state the classification for smooth modules. Okay. Oh, did I have that result? Well, anyway, I may not have this result. So for this Varasolo superalgebra, for this Varasolo superalgebra, we have the similar result. We have the similar result for the simple for the Varasolo superalgebra. Okay, for the simple modules over the Varasolo superalgebra. Okay, I may have it. I forgot. Okay. Yeah, this is for. Oh, yeah. I have this one. I have this. Sorry. So here, this is the classification result for simple smooth modules for Navier-Schwarz algebra. The algebra exactly what I introduced this as. So yeah, the theorem tells us any simple smooth S module is a highest weight module or isomorphic to the induced module from V for a simple S0 module V, such that for some positive integer k, Lk acts on V injectively, and Li acts on V is equal to 0 for all I bigger than k. Well, this condition implies that Gi minus half V is equal to 0 for all I bigger than k. Okay. Yeah, this is it's almost the same with as the Varasolo case, okay, the super Varasolo. Well, this is one of the Varasolo superalgebra. The other Varasolo superalgebra is called what do we call it? This is called Ramod. I forgot the name. So anyway, this is for half. Well, we have the other Varasolo superalgebra. Okay. But for the other algebra, we don't have we don't have any result for simple smooth modules. Okay. I hope we have similar results like this, but so far we don't know. But this is for the mirror Heisenberg-Varasolo algebra. Okay. Yeah, let's look at this this result. Yeah, let V be a simple. We define this D0 negative n. This 0 means the index of L is bigger than or equal to 0. And negative n, this is the index of say H, right? H, the index is bigger than or equal to negative n. Well, actually here we have the index of H is an integer plus half. Okay. And this is the mirror Heisenberg-Varasolo algebra. Maybe I just recall the mirror Heisenberg-Varasolo algebra. Yeah, this one. Okay, so we have the half index here. Oh. We have only two-dimensional center for this algebra. Okay. This is a construction result. Yeah, let V be a simple D0 negative n module for some positive integer n. And C is a scalar such that C1 on V is a scalar C, C2 on V is 0 on the capital V. Assume that we have an integer k bigger than or equal to -n satisfying the two conditions. Yeah, the action of h k plus half on v is bijective. And then h m plus half v is equal to 0 and dm plus n on v is equal to 0 for all m bigger than k. Okay. And then the induced module, the induced d module, this one is a simple module. Okay, v is simple, then the induced module is a simple module over d. Okay. So here this k, let me see, this k is, well, we assume that the C2 is 0. Okay. Yeah, we also assume, yeah, this one is bijective. And now we can have the classification theorem. So every simple smooth D module of level 0 is isomorphic to a smooth Varsola module with edge x on s is equal to 0, or s is the induced module you saw in the previous theorem. Now, yeah, the first part, S, so simple smooth module is just a simple smooth module over the Varsola algebra. Yeah, the other, the Heisenberg part, the mirror Heisenberg part, the action is 0. Okay. Yeah, the second part is an induced module. Okay. Yeah, here this is definition. So if V is a Varsola module, it's a module over the Varsola algebra, then V can be viewed as a D module by defining H act on V to be 0. Yeah, generally we write this new module as V to the power of D. Yeah, making V to a module over the big algebra. But we can do this because H is an ideal of the algebra D, the Lie algebra D. Okay. Okay. Now, yeah, before I give you the result for non-zero level, I need to introduce some infinite operators. In this book, it's a huge book, and they studied, they have those operators, but they only consider highest weight modules over the Heisenberg algebra H. Okay, over the Heisenberg algebra H. Now we can generalize the result, those operators, to smooth modules over H. Those operators are well defined, and also they satisfy the same relations. Okay. And we generalize their results. Okay. Yeah. Well, we don't need to verify those relationships. Okay. Now, in this preprint, we have the classification. Oh, well, here this is the construction. We don't need to understand this, and now we need to have this simple smooth module classification. Okay. So here, let S be a simple smooth module over the mirror Heisenberg-Varsola algebra D with level L non-zero. That means the action of C2. We know D has two centers, C1, C2. C2 is the Heisenberg algebra center. That center, the action is non-zero. It's a scalar. We know simple modules. For simple modules, we know the centers, the action are always scalars. Okay. Yeah, S is a simple smooth module over D with level non-zero, L non-zero. Then we have three cases. S isomorphic to H to the power of D, where D is a simple smooth module over the Heisenberg algebra. Oh, I don't think I introduced this. Yeah, I did. I didn't explain this one. Say we have this Heisenberg, restricted Heisenberg module H, right? We have the center, the action is a scalar L. After those, say, yeah, after D acts as this operator, D0 acts as this operator, and HR acts on HR, and C1 acts on 1, C2 acts on L. And then after those operations, we can make this H into a D module. This module, we write it as H to the power of D. Yeah, that is definition for H to the power of D, okay? So here's the classification theorem. Yeah, S is a simple smooth module over the mirror Heisenberg universal algebra D with level L non-zero. Then S is isomorphic to H to the power of D, where H is a simple smooth module of the Heisenberg algebra. Okay. Or S is an induced D module from a simple smooth D0 negative N module for some positive integer N. Or S is a direct product U to the power of D and H to the power of D, where U is a simple smooth versal module and H is a simple smooth module over the Heisenberg algebra H. So we have the definition for U to the power of D and H to the power of D is the same thing with that. Okay. So we have this over the mirror Heisenberg universal algebra D, the simple smooth modules are these three forms. Okay. Okay. Now I give you the following result. Well, from the definition for smooth modules, and well, the definition actually is not easy to verify. You need to verify many, for each vector. It looks complicated. Yeah. But here, actually, I'm going to explain a little more on this theorem. Yeah. To say if you consider highest weight modules, but actually, we don't have the second class. So this class actually we do have for highest weight modules we always have the first case or the third case. Well, the first case can be considered as the first case by taking U to be a one-dimensional module. So for highest weight modules, any smooth module, any module can be a direct product of the versal algebra and a module over the Heisenberg algebra. But here for smooth modules, actually we have some simple modules that are not, they cannot be a product, a direct product. Okay, we have examples. Okay, now I'm going to show you the following interesting result. The theorem is proved by Gao Xu and Yuqiang Zhao. Okay, they proved the following. Let S be a simple module of the mirror Heisenberg algebra D, Heisenberg versal algebra D, such that Dn acts on S locally nilpotently for one positive n, for one positive integer n. Then S is a simple smooth module. So that means they need only, well, this is only this for mirror Heisenberg versal algebra. Actually, this is also true for versal algebra. I will explain a little bit later. So you need only to verify for some positive integer n, Dn acts on this S locally nilpotently. Yeah. Okay, yeah, this is the yeah, something we know. Now let me give you the characterization for simple smooth modules. Well, basically, yeah, it's the following theorem. Yeah, let me be a simple module over the versal algebra. If we can find a positive integer k such that dk acts on V locally finitely, then V is a smooth module. Well, the last theorem tells us, let's say, dn locally nilpotently. Well, locally nilpotently certainly implies locally finitely, but locally finitely doesn't imply locally nilpotently. Okay. So here, this theorem is stronger. Okay. So that means you need to verify much less to see a simple module to be a smooth module. Now, actually, this theorem is not only for versal algebra, for many algebras. There are some algebras people already did some results for smooth modules. This is one. The planar Galilean conformal algebra, G, is a complex Lie algebra with a basis. Now we have Ln, Hn, In, Jn, and n is running over integers, satisfying those relations. So here we don't have center. We don't have center. Yeah. So Lns, they form the centerless versal algebra. L and H, you can see this is the centerless Heisenberg algebra. Okay, Heisenberg algebra. Right? L and I, that is called, just say L and I, that is called the W22 algebra. W22 algebra. Let's see L and J. L and J. Yeah, this is the same. You have two copies of W22. You have one copy of Heisenberg versal algebra. Now the action, say H on I, you get J, H on J, you get I. So H0 is no longer a center. Basically, this Lie algebra doesn't have any center. This algebra, yeah, is centerless, right? Okay. So there's some papers constructing simple smooth modules over this algebra. I also give you this. This is called Ovsenko-Roger algebra. L. It is a complex Lie algebra with a basis. See here, Ln, Fn. And you have three centers. N is running over all integers. The bracket was first line. That is the versal algebra with center C. L on F. This is a little bit different. It's minus m plus n times Fm plus n. And then plus, well, you have two-dimensional center, MC1 and plus C2. So this algebra has three-dimensional center, C, C1, C2. And Fn is a commutative subalgebra. Okay. So here you don't have a Heisenberg algebra in this Lie algebra. You don't have a Heisenberg subalgebra. Okay. This algebra is centrally closed. It's centrally closed. Okay. Now I need to also to recall affine algebras and affine versal algebras. So G here we take G, a simple finite dimensional Lie algebra G. We fix the Cardan subalgebra H. Suppose third is a set of roots of G, and third plus is a set of all positive roots of G with respect to H. Then we have the root space decomposition. G is equal to H, direct sum of all those G alphas. Okay. And on G, we know we have the Kac form. The Kac form. This is a non-degenerate symmetric bilinear form. Invariant bilinear form. Yeah. Let's recall the loop algebra G hat. Basically, G hat is the central extension of the loop algebra G tensor, the Laurent polynomial in variable T. The brackets say here we use x, m, x, y, n. That is x, m, y, n is the simply for this x tensor T to the power of n. Okay. X, m, y, n, that is x bracket with y, m plus n. And here we have m times, this is times the Kac form of x and y, and then delta m plus n 0 times k. K is the center. K is the center. So this is the centerless affine Kac-Moody algebra G hat. The affine Kac-Moody algebra, we should add one more element. This is the derivations. dx on xm simply is equal to m times xm. Okay. Yeah, this is our affine, untwisted affine Kac-Moody algebra, G hat. Now we also have the affine Varsala algebra. The affine Varsala algebra, that is the Varsala algebra tensor direct sum, G hat. Well, this one is a Lie algebra, this one is Lie algebra. And between these two, the bracket is given by the following. dn xm is equal to m times x m plus n. Okay. Yeah, then we know all the brackets in this Lie algebra. Okay. Now, Varsala algebra has a one-dimensional center C, and this G hat has one-dimensional center K. So we have two-dimensional center for this affine Varsala algebra. Okay. And also we have the degradation for the affine Varsala algebra. Okay. Basically, this is with respect to D0. Okay. Now we can have the following theory. This is the characterization for smooth modules. Yeah. Suppose G is any algebra among the twisted Heisenberg-Varsala algebra, the mirror Heisenberg-Varsala algebra, the planar Galilei conformal algebra, Neville-Schwarz algebra, affine Varsala algebra, the Ovisenko Roger algebra, defined as above. That will be a simple G module if there exists a positive integer k such that Lk, or some cases dk acts on V locally finitely, then V is a smooth module. Okay, so here I said V is a simple G module. Okay, we need only one element, Lk. We check if we can find one element, Lk acts on V locally finitely, then we can conclude that V is a smooth module. Okay. Yeah, so here among the algebras, Lie algebras, actually we don't have the affine Lie algebras. Yeah, you may ask, so how about the affine Lie algebras? Next, I'm going to talk about this. Yeah, the affine Lie algebra, we have this detailed, we have the degradation with respect to D or D0, right? Yeah, this detailed K simply G bracket K. And if K is 0, including two centers. No, the center K and D, the derivation D. But the other center actually, yeah, I think here we need another center 0, right? Yeah, no. Yeah. Yeah. So here I lost one, I missed one center. Yeah. Okay. Now we have the similar result. If there exists a positive integer K and a non-zero H in the Kazhdan algebra of the finite dimensional algebra, such that HK acts locally finitely on a simple G-tilde module V, then V is a smooth module with respect to the above Z gradation. Okay, Z gradation is this Z gradation. So you have a simple module over G-tilde. We only check for some H, some K. This element acts on V, whether acts on V is locally nilpotently. Okay. But here you may, a careful reader you may find, so here we use locally nilpotently. Okay. Can we use locally finitely? But actually we cannot do that. We have counterexamples. So the counterexample shows us there are some simple modules which are not smooth modules, but HK acts on V, not locally. No. Well, we have examples, say, what is counterexample to this theory? So V is smooth module. Well, yeah, if HK acts, yeah, we have some counterexamples. V is a smooth module, but HK, any HK acts on V not locally finitely. Not locally, not locally finite. Yeah, not locally finite. Some HK, sorry, some HK. Yeah. So this is actually the corresponding result for the affine algebra. Okay, we cannot use, but here, no. Here we cannot use locally finitely. Okay, we have counterexamples. Okay. Now, yeah, you may ask, say, do we have some examples, simple modules over some algebras? Say that, say all those dk, right? For this, yeah, all those dk or lk acts not locally finitely. Yeah, we do have some examples. Yeah, this one. This is the example of simple modules over the versatile algebra, where all dk don't act locally finitely. Okay. Now we need two parameters, lambda a. This lambda is non-zero. A is just a complex number. And on this polynomial algebra in one variable, we can define the action of the elements of the versatile algebra. Say dn acts on t to the power of j is simply lambda to the power of n, t minus an. A and n are scalars, times t minus n to the power of j, and c acts on tj is 0. Okay. This module looks complicated, but we can simplify it. Well, first, this module omega lambda a is simple if and only if a is non-zero. Okay. Now we can take a even better looking for form for this omega lambda a. So that means we can take both lambda a to be 1. We get a even better module. Okay. Say on this polynomial algebra, we have the action dn acts on tj simply t minus n to the power of j plus 1. C, the action of c is trivial. Okay, it's a very nice module over the versatile algebra. It's very easy. It's very easy. Okay. Yeah, I guess this is the simplest module over the universal algebra. Yeah, this module is simple. This module is simple. It's very, yeah, very nice. It's a very nice module. Okay. Okay, so thank you very much. I think I stop here. I went very quickly. Yeah.
Okay. Thank you very much for your interesting talk. Are there any questions, comments, or
Yeah, there's some questions. Yeah, said motivation for the terminology.
in the chat?
Yeah, the chart for smooth modules. Yeah, so you're right. Smooth modules are coming from geometry. Yeah. So like let's see. How come it doesn't work? Like the very beginning in this paper, actually they study some geometry, algebraic geometry, and also yeah, these two papers they use the topology. Well, they use formal power series because they use using those they have a good topology. Yeah. But here, Rudakov didn't call them smooth modules. They call he called those modules as continuous modules, simple continuous modules. Okay.
Okay. Any other questions? Okay, please, Alberto.
Yes. Hi, Kaiming. Very nice talk.
Yeah, thank you very much. Yeah.
Are there classifications or descriptions of smooth modules for, let's say, affine Kac-Moody algebras?
No.
Because your result is about.
This is here. Yeah. So we only know the classification for the Varsala algebra, the Varsala superalgebra. Only one of the Varsala superalgebra, not the other Varsala superalgebra. Yeah, and also for this one, Kazhdan have WSH over formal power series. Yeah, only these three. Yeah,
and there are at least nice examples of smooth modules for affine Kac-Moody algebras. Nice constructions of these modules.
Yeah, most of them are like here over these superalgebras. Besides highest weight modules, all other smooth modules are not weight modules. They're not weight modules. Yeah, they have some nice. They have some nice. Let me see. Maybe the end. How come? I don't know. Oh. Like the induced module. Yeah, the induced module. The induced module they have. Let me try to maybe.
Yeah, in many results, either there were highest weight modules or they were induced from some nice.
Yeah, if you consider, yeah, say here, this is the easiest paper maybe. So you take say the Varsala algebra, right? The Varsala algebra, you take say we use D, say D0, D1. We have this two-dimensional solvable Lie algebra, right? You take weight to be a infinite dimensional module, simple infinite dimensional module over D0, D1. And then you consider the induced module. Well, certainly this way, the actions of the D2, D3 on weight are 0. Yeah, so, well, the structure is kind of simple. It's kind of easy. Yeah, the induced module, yeah. But talking about, say like, we have, so simple, where are plus modules. Basically, here we use this way actually is a simple module over a finite dimensional solvable Lie algebra. But unfortunately, we don't have such classifications. Well, Bloch's paper Bloch has a long paper in 1981. In his paper, he gave all simple modules over SR2, right?
Mhm.
But besides SR2, say SR3, well, no one knows all the simple modules. Yeah. Yeah, very nice question. Yeah, we don't have.
Okay, thank you very much.
Thank you.
Thank you. Any other questions? Okay, if not, let's thank Kaiming again.
Yeah, thank you very much. I'm happy to be here to give this talk. Okay.
Thank you. So we will resume on next Monday at the usual time. Bye. Bye, everybody.
Yeah. Bye-bye.
Bye.